All right, so I'm now going to prove the Fourier Inversion Formula. So let me just give the Fourier formula. So f hat of omega. So we're thinking about f as being a function of the variable x. The Fourier transform is a function of the variable omega. So this is 1 over the square root of 2 pi times the integral x goes from minus infinity to positive infinity, f of x e to the minus I omega x dx. Okay, what I'm going to tell you about today, or not today, well, I mean, yes, today, but in this video, I'm going to tell you more, I'm going to tell you more things today than just this. But the Fourier inversion formula says the following. It says that f of x is equal to 1. Actually, let me define it this way. So, the Fourier inversion, g hat, or g check, notice it's an upside down hat, is equal to 1 over the square root of 2 pi times the limit omega equals minus infinity to positive infinity g of omega. Then it's going to be e to the I omega x, so there's not a minus sign here, d omega. So the Fourier, this formula is called the Fourier inversion formula because it does the it's the inverse Fourier formula, but we haven't proven that yet. So g check of x, this is a check instead of a hat, g check of x is equal to 1 over the square root of 2 pi times the omega integral, omega going from minus infinity to positive infinity, g of omega e to the I omega x d omega. Okay. What we're going to prove, I don't know how many videos this will take, definitely one, maybe two, depending on how long things get. What we're going to show is that f of x is equal to 1 over the square root of 2 pi times the omega integral, with omega going from minus infinity to positive infinity, of the Fourier transform of f. So there's f hat of omega, and then e to the I omega x, and we're integrating with respect to omega, so we've got a d omega there. Okay, so we're going to prove this. And unfortunately, it takes... one of the main steps of the proof, I'm just going to tell you, like, that a certain fact is true, and it's going to be kind of a crucial moment in the proof. It's a little complicated. It goes a little bit beyond what we're doing in this class and kind of the background that many of you have. But I highly encourage you to try to figure out why this is true. Read a proof about why this fact is true. Okay, so what I want to show, or what I want to use, is the following fact: f of 0 is equal to the limit as n goes to infinity of the integral going from minus infinity to positive infinity, f of x sine of nx over pi x dx. Okay, now I want to point something out here, okay? And the thing that I want to point out, sorry, I'm now rambling so I can find my pages. The thing that I want to point out is this is true, but we are not allowed to move this limit on the inside of the integral here. And the reason is, if we think about what happens if we move this limit on the inside of the integral, this is no longer defined. As n goes to infinity, sine of nx over x, that limit doesn't exist. Okay, aside for x equals 0, that limit doesn't exist for any x other than x equals 0. So this is a case, in previous parts of your math education, you've been warned about times when you're allowed and not allowed to interchange the limit and the integral. Like, for example, Taylor's series. This is a case where you're not allowed to do that. You are not allowed to exchange this limit with the integral. This fact is true. If you put the limit on the inside, it becomes meaningless because this limit doesn't even exist. Okay, and I'm about to erase this and write something that is more general than this fact. And it's going to be the following. It's going to be that, actually I'm going to write it up here. I'm going to rewrite what I had, sorry. F of 0 is equal to the limit as n goes to infinity of the integral minus infinity to positive infinity f of x sine of nx over pi x dx. I just rewrote what I had before. Now, in general, f of x naught is equal to the limit as n goes to infinity. This integral goes from minus infinity to positive infinity. F of x sine of n times x minus x naught over pi x minus x naught dx, and we can shift it the other way and say this is equal to the limit as n goes to infinity minus infinity to positive infinity f of x plus x naught sine in x over pi x dx. Okay, and again, I'm starting with this, and from this fact you can get to that fact. I'll let you figure out how that might go. What I'm saying, I want to point out one more time, we cannot move the limit inside the integral like this. I'm just giving you this fact. I want you to learn why this is true, but I'm just giving it to you for now. We cannot move the limit inside the integral here. This is something that's important. But notice what's happening. Notice what other thing has this same property. It's the Dirac delta function. Notice that f of x naught is equal to the integral minus infinity to positive infinity of x plus x naught times delta of x dx, or we could write this as the integral from minus infinity to positive infinity f of x times delta of x minus x naught dx. Sorry, I was getting a lot of text messages. Okay. So now what we're saying then, in a certain sense, we're saying the limit of these sine functions is equal to the delta function. Okay, so what I'm saying, let me write this. What we're saying then is that the integral minus infinity to positive infinity f of x plus x naught, or sorry, let me write it the other one. F of x delta of x minus x naught dx is equal to the limit as n goes to infinity. Running out of room here. X minus infinity to positive infinity f of x sine n times x minus x naught over pi times x minus x naught, and then dx here. Sorry about that. Okay, so in a certain sense then, we're saying that the delta of x minus x naught function is equal to the limit as n goes to infinity of sine n of x minus x naught over pi times x minus x naught. Okay, but the limit it's not a pointwise limit of functions here. Okay, in other words, I'm not saying for every x you put in here, you're going to get this, or for every x naught you put in here, you're going to get that, or anything like that. This is not a limit that you are probably used to seeing. It's not a pointwise limit. It is a limit in this sense here. It's a limit meaning if we integrate this, we get this same integral. Okay, but we have to have the limit on the outside of the integral. And so when we do that, we say that sine of n over x minus x naught over pi times x minus x naught converges weakly to delta of x minus x naught. So when we talk about one sequence of functions, sign in, this is a sequence of functions. When we say it converges to another function, typically we mean for every x you put in here, you get the same thing over there, okay, in the limit. That's not what converges weakly means. Converges weakly means it only converges in this kind of weird or new integral sense. Okay, so when we say that this limit exists, we have to recognize that when you write it, this limit here does not mean a pointwise limit. It means this integral way of looking at things. Okay, so how can we use this to prove this Fourier inversion formula? Well, there's a couple of things before we can do that. There's another fact that I want to share with you. Write it over here. Sorry, I'm just running out of room a little bit. Okay, so this is just like an integral that you can do on your own and show that 1 over 2 pi times the integral, the integral omega going from minus n to n of e to the minus I omega x d omega. You can show that this is equal to sine of nx over pi x. We've done similar computations. Use Euler. We did a very similar computation. This is the exact computation, in fact, we did when we proved when we computed the Fourier transform of that rectangle function. Okay. And so now what I want to prove, what I'm going to show over there, is that f of x is equal to the inverse Fourier transform of the Fourier transform of f. In other words, to be explicit, this is 1 over the square root of 2 pi times the integral omega going from minus infinity to positive infinity f hat of x e to the positive I omega x, and then we're integrating with respect to omega. So that's what I'm going to prove now. Okay. And again, one thing that we want to assume here, we're assuming that f and f hat are continuous and integrable. Okay. So how can we prove this? Well, I'm going to start off. If we look at this formula here, sorry, that should be an omega. If you look at that formula there, I'm going to start with this formula. That's what I want to show is equal to f of x. F hat of omega, e to the I omega x d omega. My goal is to show that that is equal to f of x. Okay, well, what I'm going to do next is I'm just going to substitute the integral for f prime or f hat of omega there. So this is going to be 1 over the square root of 2 pi. We're going to have the integral omega equals minus infinity to positive infinity. Now the integral for f hat of omega, so typically we would use the variable x, but we're using the variable x there. So I'm going to use the variable s as my integration variable. So this is the integral s equals minus infinity to positive infinity. And we've got f of s e to the minus I omega s ds, and then I'm going to multiply it by e to the I omega x, and then d omega. Okay, now we need to be careful here. We want to change the order of integration. That's one of the things that we want to do here. But we need to be a little careful with that because we can't just willy-nilly change the order of integration. And the reason is because these functions are not absolutely integrable in both variables. See, what I mean is the following. So this is equal to the limit as n goes to infinity, 1 over the square root of 2 pi, and then we're going to look at the integral omega equals minus n to n, and then have the integral s equals minus infinity to positive infinity, and we're going to have f of s e to the minus I omega s, and then e to the I omega x. The inner integral is ds, and the outer integral is d omega. Now, what's going to happen is it's not at all clear if omega is going from, if I have this omega going from minus infinity to positive infinity, and I swap the order of integration, I'm going to be integrating that function as a function of omega from minus infinity to positive infinity. If I didn't do this limit right here, if I just tried to swap the order of integration here, what I would be ending up with is something like the integral omega going from minus infinity to positive infinity, e to the minus omega x, e to the I omega x. Now, whatever this function is, d omega. Now, notice this is an exponential function. It's going to be, we can combine this, this is I omega s here. We can combine this into one function or one exponent, and we have e to the I omega times x minus s. Now, this is a function, it's a complex valued function, and if you just try to do the antiderivative, you'll see that it doesn't make any sense, or it doesn't exist. Like this integral, as I've said, as I've expressed it here, this integral doesn't exist because the limit of the antiderivative of these terms, as we go to minus infinity plus infinity, don't exist. Okay, so I'll let you think through. If you think this exists, try to compute it, and you'll see that you're going to end up having to compute something like the limit as omega goes to infinity of this right here, and that limit just doesn't exist. Okay, so this function, this integral does not exist, so I can't just swap the order of integration here. However, if I limit my omega integration to go from minus n to n, I can swap it. I no longer have that problem. And the reason is I'm integrating over a bounded domain as far as omega goes, and the functions I'm computing are continuous, which means they're bounded over omega. Sorry, gotta wiggle my, no. Okay, sorry, my computer went to sleep there. Okay, if I look at the omega integral when I'm integrating, excuse me, so for me to be able to swap this order of integration now, this function, if I take absolute values, needs to be absolutely integrable. And it is. It's integral in the omega variable because we're integrating over a bounded domain, and the omega function is bounded. It's a function whose complex modulus is bounded by 1. If I take the absolute value of this, well, I'm going to be integrating the absolute value of f of s, but by assumption, f is integrable. So in other words, if I take absolute values here, I get a function that is integrable over this s and omega domain, if I restrict my omega domain to this finite interval here. And so now I can switch the order of integration. And so now I've got the limit as n goes to positive infinity of 1 over the square root of 2 pi. And now I'm going to have s equals minus infinity to positive infinity f of s times the integral n goes, omega, goes from minus n to n. Sorry, I forgot the, oh no I didn't, okay. This is now going to be e to the minus I don't know what to write, yeah, minus I omega of x minus s. D omega ds. Okay. So what I have now is the limit as n goes to infinity, 1 over the square root of 2 pi. Shoot. I really hate to do this, but I don't. I really hate to do this, but I've made a mistake here. 1 over the square root of 2 pi. For the Fourier transform, I need to have 1 over the square root of 2 pi. Over here, so what's going to happen is when those multiply, that just goes away. That just goes away. Sorry about that. Okay, so now what I want to use, sorry about that, I'll try to remember to make a note in the description. Okay, e to the minus I omega s. So if I look at that inner integral, it's this integral right here. I've got 1 over 2 pi. If I want to move this integral over here, or the 2 pi inside the integral, you can always do that with a constant, so we're going to have this. But now, I don't have an x, I have an x minus s. Okay, so if I have an x instead of an x minus s, it's going to be this right here. Okay, or it's going to be this, but with x minus s. And so now what we get is the limit as n goes to positive infinity, the integral s equals minus infinity to positive infinity, f of s, and again, this integral right here is sine of n minus s, sine times n of x minus s over pi times x minus s, and we're integrating with respect to ds. Okay, sorry about that. So again, all I'm saying, I'm gonna circle in blue what are the things that are equal. So this is equal to that. Okay, just by using this computation over here, but instead of having an x, I have an x minus s. Okay, well now we're going to use the fact that this here converges to the Dirac delta distribution centered at x. So then this is the integral s equals minus infinity to positive infinity. And again, when we say this converges to the Dirac delta distribution, we mean in terms of this like limit on the outside of the integral sense, the weak sense. So this is f of s times delta of x minus s ds. This is just the Dirac delta distribution centered, shifted to be centered at s. So this is just equal to f of x. Okay, and so what this does, that is what we wanted to show. This is the Fourier inverse this is the Fourier inverse formula of the Fourier transform of f, and we've shown that it is equal to f of x, which is the thing that we wanted to show. Okay, so this Fourier inversion formula is going to be important to us. It's going to help us compute inverse Fourier transform. There's going to be another method we have to compute inverse Fourier transforms, and we're going to use that to help us solve differential equations.